Alright guys, welcome to our Unit 4 quiz study guide. Just going to go through this and get you guys ready for our quiz coming up. So the first thing you guys are going to need to know how to do is do the limit definition of a derivative. Now for this problem, I'm not really looking so much at the final answer as I am looking at your steps for whenever this thing is being graded. So it's kind of being graded kind of like an FRQ, if you will. Okay. So let's go ahead and get started here. When you want to use the limit definition, the first thing you need to do is you need to find out, I'm going to, instead of saying this is y, I'm going to call this f of x just so it kind of fits our other notation for the time being. So the first thing that we like to do is we like to find out what is f of x plus h, and I'm going to use h instead of delta x. I don't like delta x, it's clunky and confusing looking. So that's going to look like this. Then we need to simplify this expression. Gave you guys a little shortcut for this x plus h squared a little while back. If you want to go ahead and FOIL it out or multiply it out, you can, but that's what you would end up with there. Let's do our distribution. And at this point, we probably don't really need the parentheses anymore. So there's our f of x plus h. Okay, so I'd want to see you guys find f of x plus h in its simplified form first, of course, when you're doing this process. The next thing we're going to do is we're going to use the actual limit definition of a derivative. So according to that little process, we have the f of x plus h minus f of h, f of x over h. Okay, so I'm going to put f of x plus h first. That's the part I just found. And then in the last set of parentheses, we just put f of x as it was originally. Just like that. From there, we're going to go ahead and simplify the expression a little bit, right? So we're going to distribute the negative in here and combine our like terms. Now for this one, you don't have to necessarily make it a whole new step like I usually do. You can just change it to a plus and then change all these signs. And then that can save us a little bit of work, because now we can see that the 3x squared cancels the 3x squared, the x cancels the x, and the 3 cancels the 3. And so now we're left with this. So I would definitely want to see you guys have the limit definition of a derivative set up there. After that, the simplifying is just kind of, you should include as much as you can so that it makes sense, but there's that. After that, what we should do is we should reduce the h out. So divide every term by h. So if you divide the bottom by h, that becomes 1, so we can just ignore it. If you divide this one by h, that h goes away. If you divide h squared by h, it leaves you with 1h. And if you divide this last h right here by h, you're left with 1. Now you have to put a 1 there in this case. We didn't put a 1 here because you're multiplying it times 6x. And 6x times 1 is just going to be 6x, so we don't need it. And I'm not going to put a 1 down here because anytime you have something over 1, you don't really need to write the 1. But in this case, since you're adding a 1, that one is necessary. Make sure you have your 1 there. So as a result, I have the following. And then we just do our direct substitution. Okay, so what do I want to see whenever you guys do this process? Well, I definitely want to see that you have your f of x plus h. I would definitely want to see that you have the initial setup here And of course, I would want to see that your work from there on out, how much work you show is kind of flexible. I say kind of. It should make sense though. Okay, how you guys show your work and how much is a little bit flexible, but I should be able to see how you got from this step up here to down to here. Okay, I'm not looking just at the answer. That's pointless because I know you guys can just do the shortcut, right, to find the derivative. But so it's not the answer that I'm impressed with. It's more like I would definitely want to see this. I would definitely want to see this setup, and your work should make sense as you work your way to the final answer. Okay, and so that's kind of how I'll be grading these. Let's go ahead and take a look at the next one. So same stuff, right? I'm going to call this f of x. Okay, so the first thing I want to do is find f of x plus h. And for this one, there's not really a whole lot of simplifying. That's about it for that. Now we're ready for our limit definition. Oh, shouldn't be x, my bad, it should be h. There we go. In fact, I think I'm going to make this a little bit shorter. Okay, so there's your setup. So once again, I would definitely want to see your f of x plus h. I would want to see your setup. But after that, we got our steps, our algebra to go through to get us to our final answer. And for this one, I would definitely want to see that you're multiplying by the conjugate. So I'm going to have to write really tiny here to squeeze all this in. But basically, it's going to look exactly the same, with one little difference, right? And that little difference is we're going to have a plus here in the middle instead. And whatever you do to the bottom, or the top, I mean, you're going to have to do to the bottom. Okay, so we want to see that. And so when we multiply these together, we've talked about the fact that basically you're just going to do this thing times this thing. They're identical, and so when you do that multiplication, the square root just cancels out, and you're left with everything underneath of the square root. So that would be 5x plus 5h plus 4. I would put parentheses around it at first. And then we do this thing times this thing. And so, once again, they're identical. So you get the same thing. It's just no more square root, but we do parentheses. And since this one was negative, when you multiply a negative one with a positive one, it's still negative. So there's that. Okay, and on the bottom, we have h, and then we have this whole thing here. All right. At this point, we're going to go ahead and distribute the negative. And the 5x's are going to go away, and the 4's are going to go away. And so now I'm going to be left with the limits as h approaches 0 of 5h. That's all that's left on top now. And on the bottom we have h, and then we have this big old square root thingy. Okay, and those h's should cancel out. Since I'm running out of space, I'm going to have to clear all this off. Now I'm left now with the following. And then we go ahead and we do our direct substitution. So when I plug 0 in there, that term's going to go away. And so I'm going to have 5x plus 4 plus, or I'm sorry, the square root of 5x plus 4 plus the square root of 5x plus 4. Since they're the same, we can just write our answer like this as 2 square root of 5x plus 4. And there's our final answer. Okay. So what would I want to see once again? I would want to see what was your f of x plus h, which was the very first thing I did. I would want to see the setup, and then from there, I need to see the math or the algebra that you're doing that gets you to the final answer. Okay, so looking for those same three things once again when I'm grading these things. All right, let's go ahead and take a look at one more of these. This one is one of the ones that have fractions in them. All right, so once again, f of x plus h is first. Simplified, of course. And we have our setup. These in parentheses. So at this point, I would probably just distribute this negative into here, make this a plus, right? So double negatives becomes a positive there. I just write it a little bit differently, honestly. So we have plus here. And what we talked about when you're dealing with these particular types of problems is we want to simplify the complex fraction for these ones. So I'm going to multiply this thing by 2x plus 5. And my purpose of doing that is so that those will cancel out. But you have to do it to every other term as well. Okay. And just for clarity, I'm going to rewrite it now and what that would look like if it's all been simplified. Okay, and so now we're going to go ahead and multiply everything by the other little denominator there, the 2x plus 2h plus 5. So I'm going to put it up here just because I don't have a lot of place to squeeze it in. Oops. So this one will cancel this one when I multiply that on the top, but we have to put it everywhere else as well. So let's see what we have now as a result of that. We would have here it's just going to be negative 2 times the parentheses 2x plus 5. Next we're going to have a positive 2 being multiplied by the parentheses 2x plus 2h plus 5. And then on the bottom we have h, 2x plus 5, and 2x plus 2h plus 5. So I don't know if you guys are catching on, but it's very similar how it always works out basically every time. If I were solving these problems on my own, I could actually jump straight from this step to this step. And the reason why is because the same thing happens every time. This piece goes there, this piece goes there, oops, too far, right there, and then both of them go down here. So it's kind of simple. It always works out exactly the same. So I don't mind if you guys just jump from that step to the other. You don't have to show this process of multiplying if you don't want to. To me, I feel like it's kind of evident, and so not necessary. But feel free to show as much of that work as you want to. But there's that. But we're not done. We got to keep going. So at this point, distribution comes next. And so that's going to give me the limit as h approaches 0 of negative 4x minus 10 plus 4x plus 4h plus 10 all over this good stuff down here. All right, and the 10s cancel, the 4x's cancel, and I'm left with 4h on the top now. And this h will cancel that h. That's removing the discontinuity. And then we can go ahead and plug in the 0 over here, which is going to make that 2h go away. And I've got 2x plus 5 times 2x plus 5 on the bottom and a 4 on the top. So we can abbreviate that as 4 over 2x plus 5 squared. Final answer there. Okay. There it is. There it is. Okay, so that's using the limit definition of a derivative to find a derivative. For numbers 4 through 6, we're going to use the alternative form. And for these ones, it's about finding the derivative at a specific point. All right, so for these ones, what you want to start off by doing, once again, I like to think of this as f of x. I like to start off by finding f of the number that they want us to plug in. So let's do that first. Exponents are first. Be careful with your order of operations. Followed by multiplication. And then addition and subtraction from left to right. And so f of negative 1 is negative 2. So we have our setup. Now the setup for the alternative form for the limit definition of a derivative is as x approaches the number that you're plugging in, you have your f of x minus your f of c, which in this case is negative 2, all over x minus your c. Okay? So for this one, at this point, what you're going to do is you're going to do a couple things. You're going to start by simplifying the numerator and denominator. So in this case, that's going to become plus 2. And you're going to combine it with the negative 4 to make minus 2. In the bottom here, that's going to just become plus. The next thing that you're going to do is you're going to, if it's a polynomial like this one or a rational expression, what you're going to do is you're going to factor to simplify it. It's supposed to be a square. All right. So let's see. I want to get 2 there. 2 and 1. All right, I think that'll work. Here we go. All right. Then the next thing we would want to do is remove the discontinuity. And that leaves me with this. And then the last step is just to do some direct substitution. Okay, And that's it. So that's the alternative form of the definition of a derivative in order to find the derivative at a specific point. So what would I want to see in this one? Well, I'd want to see that you've got your f of -1, of course. I would want to see that. I would definitely want to see your setup. And then once again, I'm going to want to see your algebra, how you got from here all the way to this answer, and how much work you show is flexible. I'm okay with that. But you do have to use, for these particular problems, you do have to use factoring in order to get there. Technically, you could use L'Hopital, but I don't want you guys to use L'Hopital for these problems. The reason I don't prefer you to use L'Hopital is simply because L'Hopital assumes that the derivative exists, and here we're proving that the derivative exists. So I just want you guys to do the factoring strategy. Okay. All right. Let's go ahead and we'll move on to the next one. Similar steps. The algebra process is a little bit different. So the first thing I want to do is I want to find out what's f of -8. Okay, so f of -8 is 6, so I'd want to see you get that. Then I'd want to see your setup for the alternative form, which would be x is approaching -8. Then you have your f of x minus your f of -8 all over x minus the -8. Okay, so for this one, I don't think we need to show a whole lot of extra steps for simplifying. I think we can just, right now go ahead and replace the double negatives here with a plus. I don't think we really need the parentheses here. They don't really serve any purpose. So that's pretty good. Let's go ahead and do the next step. So now the next step is to actually find this limit using the algebra techniques. And so for square roots, the algebra technique that we use is the conjugate. So we're going to multiply the top and the bottom by -4x plus 4 plus 6 instead of -6. Put that in parentheses. Okay, put that in parentheses also. Okay, so we do first times first, cancels out the square root, but we'll go ahead and we'll keep the some parentheses on there, and we'll be left with -4x plus 4, and then -6 times a +6 is -36. Bottom we're going to leave the same for now. All right. Simplifying what we got going up here on the top, the -36 and the 4 need to be combined. All right. Now at this point, if you can't remove the discontinuity, then we need to factor the top. So in this case, I can factor something out of the top. Both of those can be divided by 4. In fact, they can both be divided by -4. So that's what I'm going to do, is I'm going to take a -4 out of there. And then we can remove that discontinuity. All right. Next, we're going to go ahead and I'm just going to rewrite it really quick. You don't have to do that necessarily yourself, but I'm just trying to be clear with my work. So this is what we have as a result of all this. And at this point, I would do the direct substitution. So plugging that in, -4 times -8 is going to be -32. I'm sorry, positive 32. Positive 32 plus 4 is 36, and the square root of 36 is 6. So we have 6 plus 6, which is 12 on the bottom. And then when we simplify that, we end up with -1/3 as our final answer. Okay, so once again, you need to see your f of -8. I would need to see your setup, and then I would need to see some kind of work that's going to get us from point A to point B to get to that final answer. And your work should make sense, okay? If it doesn't, you could lose points there, so you don't want to be too skimpy with the work. Now for numbers 1 through 6, you guys, just so you know, I'm going to have one problem like 1 through 3 and one problem like 4 through 6, just because these do take a little while, so I'm not going to have too many of these types of problems, but you do want to make sure that you know how to do one problem from each of the first 6 problems, first 3 and the second set of 3. Okay, next one. This time we're finding f of 0. And it's just going to be 1. Okay, so my setup then is going to be limit as x approaches 0 for my function -1 all over x. Now you could write -0 if you want to, but x minus 0, well, that's just basically x, isn't it? So in this case, we're just going to leave it as x. And that'll make the canceling out that we have to do in a second a little bit more obvious. So we have a complex fraction. So what do we do when we have complex fractions? We multiply everything by the little denominator. So I'm going to multiply everything by 2x plus 1 so that these cancel out. Okay, as a result of doing that, we will have the limit as x approaches 0 of 1 minus 1 times 2x plus 1 all over x times 2x plus 1. Next, we're going to distribute the -1 into the parentheses. The 1s are going to cancel here because 1 minus 1 is 0. Now I'm left with -2x over x times 2x plus 1. And these x's cancel each other out by division. And that removes the discontinuity. And then we go ahead and do our direct substitution to get our final answer. 2 times 0 is 0. 0 plus 1 is 1. So we're left with -2 over 1, which is just -2. All right? And so that's the alternative form of the limit definition of a derivative. Let's go ahead and continue our journey here. So for number 7, part A, I want to know what's the function. Well, what we're going to do on these is we're going to ignore the h and we're going to replace the number with an x. And so the function in this case is the square root of x. Part 2, identify the c value. At what value are we trying to find the derivative? And that's going to be the number that we crossed off there. So the c value is 2. For part C, they want us to actually find out what f prime of c is. So the first thing you're going to do is you're going to take the derivative of this expression, which is 1 over 2 square root of x, and then you plug in the c value that they gave you. And I'm just going to leave my answer like this, honestly. It doesn't really simplify. You could rationalize it if you wanted to, but I think I'm going to go ahead and just leave it just like that. All right, let's go ahead and take a look at number 8. What's the function? We get rid of the h, and we replace the number with an x. So it's going to be cosine of x is my function. We want to find what's the value of c. The c is the number that we are plugging in for x, which in this case is pi over 4. And so for to find f prime of pi over 4, the first thing I'm going to do is I'm going to find f prime of x. So the derivative of that is sine x. Actually, it's negative sine of x. And then you're going to plug in the number. And in this case, that would be negative radical 2 over 2. Let's take a look at number 9. What's the function? Get rid of the h, replace the 5 with an x. So the function is ln of x. The value of c is the number we're plugging in for x, which is 5. To find f prime of 5, we first of all need to find the derivative of f of x. The derivative of ln of x is 1 over x. And so f prime of 5 would be 1 over 5. Final answer there. For number 10, this is an alternative form of the limit definition of a derivative. So this is different from 7 through 9. These were the regular definitions of a derivative. This is the alternative form of the limit definition of a derivative. So when you're looking at these ones, the function is actually going to be this piece right here. The c value, the number you're plugging in for the derivative, is the number that x is approaching there. And then if you want to find out what f prime of 4 is, well, first of all, you would need to find the derivative of f. Now, this one's a little bit nastier. There's a few ways to do this one. You could do the quotient rule, which I'm not going to do, but you could also do, just change it to look like this, and then go ahead and do the power rule, which is the one I am going to do. So the derivative of that, you would multiply the 5 to the front. Actually, I'll write f of x here. Multiply negative 5 times 1, you get negative 5. And then take 1 away from the power, and then rewrite it again as a normal non-negative exponent expression. And then go ahead and plug in your value that you want to plug in. So in this case, I want to plug in 4. And 4 minus 3 is 1, and 1 to the 6th power is 1. So the final answer there will just be negative 5. All right. Last one here is also an alternative form of the limit definition of a derivative. And so my function is this guy right there. The value of c that we're plugging in to find the derivative is this number here. And to find the derivative, we're going to multiply the number to the front. We're going to take 1 off the power. And something I forgot to mention on number 10, but it didn't really matter, is you're supposed to multiply it by the derivative of the inside. But this problem, like number 10, it doesn't really matter because the derivative of the inside is 1, so it doesn't really affect anything, but it's something worth noting anyway. So at this point, I'm plugging in my negative 5. And negative 5 plus 4 is negative 1. Negative 1 times negative 4 is positive 4 is my final answer. All right, so later. So let's go ahead and take a look at number 12 here. Give you a big old piecewise function here. And I'm asking you guys a lot of different questions about it. So let's go ahead and jump in and take a look at what shakes loose. So for part A here, it's asking me to find the limit as x approaches -2 from the right of the function w of x. Now, this is actually a review question. This is stuff from Unit 3, but it is relevant to the stuff that we're discussing now. So if I'm approaching -2 from the right, that means I'm looking for where x is greater than -2, and that's right here. And so we'll be using this piece to accomplish this problem. And all you have to do is do direct substitution. So if I plug in -2, I'm basically going to get 1 as a result. Okay? So make sure you know how to pick the right piece out and just do the direct substitution. You're good to go. Same question, but this time we're approaching it from the left. All right, if I'm approaching -2 from the left, then that means I'm looking for a place where x is less than -2, and that would be right here. So for this one, we're using the top piece. So direct substitution is going to give me 4 minus 12 plus 9, which is 1 once again. And then part C, we are being asked to find this now. -2 from the right. But this time they're looking for w prime of x. Okay, so once again, since I'm approaching -2 from the right, that's going to be, matter of fact, let me just erase this stuff. If I'm approaching -2 from the right, that's going to be where x is greater than -2. So I'm using that piece, but this time I want the derivative of that piece. So that's going to be the limit as x approaches -2 from the right of the derivative of this, which is 2x. And my direct substitution will give me -4 as an outcome there. And then for part D, we're doing the limit as x approaches -2 from the left. And we're approaching -2 from the left. That's where x is less than -2, so that's this piece here. The derivative of that is going to be 2x plus 6, and my direct substitution is going to be -4 plus 6, which is 2. All right, so that's parts A through D. So now the question is, for part E, is this function differentiable at x equals -2? Well, in order for a function to be differentiable, you need to do steps A through D. The fact that the limit exists from the left and from the right, see how as we did it from the left and from the right, they both approach the same y value of 1. So the limit exists, okay? And the function exists also because we have an equal sign, so you are allowed to plug in -2. So we know that you don't have to write this, but we know that w of -2 is going to be the same thing as the limit as x approaches -2 of wx, and both of them equal 1. Okay, so it's a continuous function. That's the good news. All right. Now the next thing, though, for it to be differentiable is it needs to be connecting smoothly. It cannot be at a cusp. In other words, the limit from the left of the derivative and the limit from the right of the derivative have to have the same value, and as you can see, they don't. Okay, so we have a cusp when that happens. So is this function differentiable at x equals -2? And our answer to that is going to be no, since the limit as x approaches -2 of w prime of x from the right is not the same thing as the limit as x approaches -2 from the left of the derivative. Okay, so that would be our answer to part E. So basically these first four were leading up to a place where we could answer this question. And the rest of these problems are pretty much doing the same thing. Like F through J is doing the same thing, but instead of doing it for -2, it's doing it for +2. And the other one, K through O, is doing the same thing, but it's doing it for 4. So that's pretty much what the rest of these problems are going to look like. I'll go through them all in case you guys have questions, but of course you don't have to watch all of these. You can just watch the ones you want. So the limit as x is approaching 2 from the right of w of x if I'm approaching +2 from the right, I'm looking for where x is greater than 2, and that would be right here, so I'm using this piece. And direct substitution gives me 8. For part G, we want to look at what is 2 from the left. Two from the left is where x is less than a +2, which is there, and that would be this piece. And that's 1. Okay, so that's gonna, we already know our answer then to part J. Since the limit from the left and the right are not the same, we have a jump discontinuity, and as a result, this function will not be differentiable at x equals -2, but we'll get to that in a minute. Let's go ahead and move on to part H. For part H, we have the limit as x is approaching 2 from the right of the derivative. And as we said before, when you're approaching 2 from the right, that's going to be this piece. So since there's nowhere to plug the 2 into, the answer is just going to be 4. For I, we're approaching 2 from the left, and we're approaching 2 from the left, that's the top piece. Once again, they're x squared minus 3, but we're doing the derivative, which is 2x. Direct substitution gives me 4. Now you'll notice that they both have the same slope. Okay, so if these pieces were connecting together, they would be connecting at a smooth curve. It wouldn't be a sharp turn, because the slope doesn't suddenly change. But the problem is from F and G, we can see that they're not connecting. So I'll put not equals there. And therefore, this function is not continuous. Okay, so our answer then to part J is going to be no, since, now there's a few ways you guys could say this. You could say the limit doesn't exist. Because, or you could say this, and this is the reason why the limit doesn't exist, because the limit from the left and the limit from the right were not the same. Technically, you could also say not continuous, but although I'm going to allow you guys to say that in some circumstances, I think on this quiz, I want you guys to be a little more specific. So I do want you to say one of these two things. And the reason for that is because I don't want people just to take a lucky guess and put not continuous and hope they get the right answer. I want you guys to be able to prove to me that you know why. And one of those two statements there are a good proof that you actually know why. All right, so let's go ahead and move on to the last set for this, which is K through O. For K, we're trying to find Now on your quiz, you guys just, I'm not going to give you this many of these questions, obviously, right? I'm just giving you guys this many so you could see the problem from a few different perspectives. All right, so if I'm approaching 4 from the right, I'm looking for where x is greater than 4, and that would be this function here. Direct substitution there is going to give me 16. And if I'm approaching 4 from the left, that's where x is less than 4, that's here. So that would be this piece. Direct substitution gives me 16. So, since the limit from the right and the left of the original function are the same, this is looking like it would be a continuous function because the limit exists. You don't have to write this, but I'm just explaining things a little bit. Since the limit from the left and right exists, the limit is 16. Now, it could also be shown that w of 4 equals 16 because all you have to do is plug 4 in. And if you're plugging in 4, you pick the one that's equal. And so if you plug in 4, you're just going to get the same thing you got up here. So this means that the function is continuous. Those pieces are connecting together. But, like I said, you don't need to write any of this right now for your quiz or your study guide. I'm just explaining things. But let's move on to the next part. Part M is we want to find the limit as x is approaching 4 from the right of the derivative this time. If we're approaching 4 from the right, we're using the bottom piece, but we want the derivative of the bottom piece, which is 2x minus 4, and direct substitution is going to give me 4. So the slope from the right of 4 is going to be 4. As for n, the limit as x is approaching 4 from the left, that means we're approaching, where x is less than 4, so that's this top one here. The derivative of that is 4. Direct substitution, you can't really plug anything in, so the answer is just the number that's right there, so the answer is 4. And so the slope from the left and the right are the same. So not only is this function continuous and connected, but it's connected smoothly because the limit exists. So, is this function differentiable at the point? And what we would say for part O is we would say yes, since the limit as x approaches 4 of w of x is equal to w of 4. In other words, it's continuous. And the limit as x approaches 4 of the derivative from the right and from the left are the same. Okay, so for this particular one, I guess technically you could just say it's continuous. You don't need to say this. I would give you credit probably if you just said it's continuous, but I would definitely want to see that there. But just to be safe, you could write the whole thing. But that's a yes because it is continuous and because it is connecting smoothly. Okay. All right, number 13. For number 13, I'm giving you an absolute value function and asking you to find the slope of the function from the left of the cusp and from the right of the cusp. So to do this, you're going to need to write this absolute value function as a piecewise function first. Then we'll take the derivative of it and do the problem. So here we go. Piecewise function, the first thing that you're going to do is you're going to take the inside of the absolute value and you're going to make it equal 0. You're probably going to have to factor to solve for these types of problems that I'll be giving you. Then we do our number line test. We have -4 on the left and -1 here. And then we test the intervals to see whether or not we end up with a sign change. So we're going to do f of -5, f of -2, and f of 0. Just pick any number on those intervals of your number line. Okay, so here we go. So let's plug in -5. So 25 minus 25, those just cancel. And as you guys can see, there's no sign change here. Let's plug in -2 next. Four minus 10 is -6 plus 4 is -2. So that will be a change of the sign there because the absolute value will change it from a -2 to a +2. And then plugging in 0. That's going to be no change once again. And so here's my function then, written as a piecewise function. We have three intervals. We have x is less than -4. We have x between -4 and -1. And we have x is greater than -1. And we'll just put some equal signs there in the middle. It doesn't matter where you put them. And what we determined is that for all x less than -4, there was no change. So the polynomial stays exactly the same. We found that for x values between -4 and 1, there was a change. So all the signs are going to change here of this part. And then for the last one, where x is greater than 1, up here was greater than 1, there was no change. So once again, x squared plus 5x plus 4. Okay. Okay. Now, we're going to go ahead and evaluate these expressions here. I'm going to start with that one. So first of all, we need to find where -4 and from the left. So I'm looking for where x is less than -4, so that would be this one. So I would be using that piece. And the derivative of that one is going to be 2x plus 5x. I'm sorry, just 2x plus 5, my bad. And then we do our direct substitution. 2 times -4 is -8 plus 5 is -3. And just so you guys know, once you found this, the slope from the left, the slope from the right is going to be the same thing. It's just going to be the opposite sign because that's how absolute values work. It just immediately flips it. But I'll work it out anyway, just in case you were wondering why. So we want to approach -4 from the right. So if I'm approaching 4 from the right, I'm looking where x is greater than -4, so that would be this piece. But we want the derivative of that piece, so that would be -2x minus 5. Direct substitution, -2 times -4 is going to be +8, minus 5 is +3. So you're always going to get the same slope, it's just opposite signs. And the trick is basically just knowing which one's positive and which one's negative. And that comes from changing it into a piecewise function. Okay, and that's that. Let's go ahead and take a look at number 14. Find the values of a and b that make this function differentiable. So in order for this function to be differentiable, we need to have the fact that the limit of w of x as x approaches -1 from the left is the same thing as the limit wx as x approaches -1 from the right. Okay, so if I'm approaching 1 from the left, that's this piece, so I'd be using that. And if I'm approaching -1 from the right, that would be this piece. And then we do our direct substitution. So plugging in a -1, I'm going to get -a plus b. And plugging in -1 here, I'm going to get 1 minus 3 is -2 minus 4 is -6. Okay, so that's one thing you'll need to do. And that just makes sure that the pieces are connecting together. The top piece is connecting the bottom. But now we need to repeat this process, and we need to make sure that it's also smooth. And so for it to be smooth, then we need to do the same thing that we just did, but this time we're going to do it with the derivative instead. So once again, if I'm approaching -1 from the left, that's going to be the top piece, but it's the derivative this time. So the derivative of a times x is just going to be a, and the derivative of b, since it's just a number that we don't know, but it is a number, it just goes away. For the next one, the derivative of this top piece here is going to be 2x plus 3. Here we can't really do any direct substitution because we plug -1 in for x. You don't plug it in for a, we plug it in for x, and there's no x there. So the answer is just going to be a. And for this one, direct substitution, if I plug in -1 is going to be 1. So I already know that a equals 1. At this point, I have two equations, this one, and we have to put them together to solve the system. Now the way that you put them together is you're going to pick one of your equations and you can get one of the letters by itself. Now I already have one of the letters by itself here, a equals 1. After that, you're going to replace the a with whatever it equals in the other equation. So I'm going to replace the a with 1, and that should allow me to solve for b. Adding 1 on both sides, I'm going to end up with b equals -5. If you're still not done after that, you usually have to plug in something one more time to find the other variable. But in this case, we actually already have both answers. It's 1 and -5 are the final answers. All right? All right, and one more question that's required here is to determine if f of x is continuous and also differentiable at each value of x given below. If it's not differentiable, explain why. All right, so basically, if it's not continuous, it's not differentiable. So anytime there's a hole, a gap, or a jump, it's not differentiable. So right here, that's a place where we're going to have a non-differentiable point, because it's not continuous, all right? But it's possible for the function to be continuous but still not differentiable, and that's if you have one of two situations, either a vertical tangent line or a cusp. And in this case, I don't see any vertical tangent lines anywhere, but I do see a cusp. So we have 2 points where there's going to be a place where it's not differentiable, and it will be for different reasons. So let's go ahead and take a look at the problem and see what we got. So first of all, they're asking about -7. So -7 is right here. Well, at that point is continuous and differentiable. Now my directions only ask me to explain why if it's not differentiable, so I'm just going to say that's continuous and differentiable and leave it at that. But for part B, let's move on to number 3. So it says -3. That's right here. Okay, well that's a continuous point. There's no holes, gaps, or jumps, but there's a cusp there. And cusps are not differentiable. And the reason that cusps are not differentiable is because the slope from the left is not the same as the slope from the right. So the reason it's not differentiable, so you need to write your answer, is because the limit as x is approaching -3 from the right of the derivative is not the same thing as we are approaching -3 from the left of the derivative. Okay. Last one, +2. All right, well in this case, we are going to have to be a little more specific. So it's not continuous, right? So the answer is no, it's not differentiable because it's not continuous. But I do want you guys to be a little more specific on our quiz today, okay? So why is this not differentiable? Well, it's not because the function doesn't exist, because it does exist. F of 2 exists. The value of f of 2 is 0. And it's not because the limit doesn't exist, because the limit does exist. It's that point right there. And the limit of f of x as x approaches 2 is 3. The problem is that they're not the same. So that would be your explanation in this case. So your explanation for it not being continuous can be one of three things. Either f of 2 doesn't exist, or the limit doesn't exist, or they're not equal. And in this case, it's a not equal.